Well, let's talk about fasteners then a little bit. Now, fastening is the most commonplace assembly technology. Not the only one by any means, and we'll be looking at other means of assembly, for example, welding, just to give you an example, or maybe gluing something together. Fastening is something that's so obvious, so common, such a familiar experience that it deserves its own discussion, right? Fastening is also a primordial example of commercial off-the-shelf technology, and we've already seen that. And we can go to online catalogs and navigate our way through what truly is a bewildering variety of types of different technologies that can be used, and we've already been exposed to that. Okay. We use fasteners generally when we want to be able to both assemble and disassemble a part. So if we don't want a permanent assembly, then fasteners, of course, is a good place to go. Although not all fasteners are allowed for disassembly, so we'll see this as well. Okay. Now, we're not going to get into the technical details of fastening. That's its own world, as usual. Instead, all we want to do is just a quick survey of the available options and perhaps a small or short discussion on industry norms. Okay. So here in this picture, you can see. Okay, so we have essential categorizations here. Threads can be internal or they can be external. Okay, easy to see. They can also be right hand versus left hand. Now, primarily, almost always, they will be right hand, and they'll follow the right hand rule. Okay, which means that if you turn the screw in the direction of the curl of your forefingers, then the thumb will point into the axial direction of advance of the fastener. Okay. Generally, those threads will be straight. On occasion, there will be fasteners where those threads will be tapered, will be conical. Okay? That's typically the domain of pipe threading, and that matters when we want to be able to achieve a watertight fluid coupling. Turns out threads can also be useful for motion control. Okay, so you can think of a thread as a helix that's wrapped around a cylinder. Okay, so if you were to expand that in a linear fashion, then you would find that really a thread is nothing more than an inclined plane. It's really a basic machine, with a certain mechanical advantage depending upon the how aggressive the angle of the helix is. Right. However, in this context, we're going to concentrate more on threads as a means of assembly. Okay. Now, calling your attention there to the picture on the right, that's a canonical, let's call it, drawing of two threads engaging. You see the external thread there in the bottom and the internal thread in the top. Now, obviously, this is just a half drawing, so you can see the dashed dot line in there symbolizing a center line. And of course, there's a lot of terminology associated with threads. The one that we care the element that we care the most about is what's known as the pitch. Or the lead of the thread. Okay, so the pitch is very simply the distance between threads. It's also called the lead because that's exactly how much that particular fastener would advance with every turn. Okay. I'll also call your attention there to the angles. That there are many different types of threads. The ones that we're going to worry about the most, associated with common fasteners for assembly, fall under the so-called unified national standards. Okay, and those are going to have a 60-degree included angle in between the walls of the threads. Okay, so that's really the most important thing. There are other distinctions in there. You see some curving at the roots, versus a straight lines at the roots or at the peaks of the threads. Those are again discussions that are very worthwhile having, but not in the context of this particular lecture. Okay. All right, so standards. So whenever we talk about components like these, you can rest assured that there's going to be a standard availing the particular set of dimensions that they conform to. Okay. As usual, here in the United States, we have to live, with our own homegrown standard, so the American standard, and then of course the international standard that generally tends to be under the banner of ISO. Okay, so our homegrown or imperial standard is known as the UN Unified National Thread. Okay, so you will see the UN, then C for coarse, and UNF for fine. We'll see that in just a second here. But those are based on ANSI standards. They're actually historically they come from Britain, and then they end up being a harmonized standard between the United States and England. Okay. Just a quick mention that threads can be created by what's called as thread rolling. So that's a forming process, a bulk forming process where you take just a cylinder and basically press onto it the shape of the thread. Okay. Or you can also cut the thread. Okay. And that's done more as a low volume process. Okay. And the typical tool for cutting a thread is called a tap if you're talking about an internal thread, and it's called a die if you're talking about an external thread. Okay, so this is fabrication equipment that allows you to start from a blank and then cut into it the shape of the thread. There's yet a third technique, which is using a lathe. Okay. And what you do then is you have a triangular cutting tool that bites into the body of the fastener. And then, of course, as it's turning, you also have to advance the cutting tool. Of course, the process of turning and advancing at the same time gives rise to a helical pattern. Okay? And this is of interest to mention because this is exactly how threads would be generated in SolidWorks, and that's an exercise that's good to go through. Okay, to create a triangular cutting tool and then subject it to a helical path along which it would be doing an extruded cut, and that would result in a threaded body. Okay, here we see common tables readily available from the internet that gives us a window into the typical available threads. Okay, you can imagine these are going to come in very many different sizes, very fine increments. On the left in there is an American National Unified thread, okay, table, and then on the right you're going to see a metric table. The metrics are readily identifiable by the leading M in there, okay, and the American sizes are going to run as a number from 0 to 12, and then as a fraction that is going to indicate the higher sizes, and all those are going to be in inches, okay, starting at 1/4. Okay, so there's a size 0. Actually, there's even smaller than 0, and then you have again a number going up to 12. Okay, now this is the way the terminology is used, for the respective systems. Okay, so looking first at the left, the first number, that 10, is going to refer to the basic size. Okay, so the 10 in there is going to be driving the diameter of the thread, the outer diameter of the thread. Okay, the 32 is going to be the lead or the pitch, and in the English system that's expressed in threads per inch. So it's actually the opposite of the pitch. Okay, so if you take 1 inch and divide it by 32, well, that would be the pitch of a 32 thread per inch fastener. Okay, the U and F in there, UN is Unified National. The F stands for fine. Okay, so for a given size, you would have a fine and a coarse, not for all the sizes, but for most. Okay, so for example, if you look at 10, okay, there's a 1024 that would be a UNC or coarse, or a 1032, and that would be a UNF or fine. And you can see that in both cases, okay, the diameter is going to be the same, 0.19 inches. And then you're going to have different pitch diameters, fruit diameters, etc. Things that we don't need to concern ourselves with in this overview. Okay, the 2A here at the end is going to be a measure of the quality of the threads. So that's a measure of the tolerance. And there on the right you see the M for metric. Okay, the 4 is going to be the basic diameter again, but this time in millimeters, as you might well imagine. Okay, and then the 0.5 in there is going to be not the thread count, but rather the pitch. Okay, so instead of threads per inch, in this case, it's just going to be the millimeter pitch or the millimeter lead. So how much the screw will advance with every turn. And similarly, the 6E in there is going to be a designation for the quality of the thread. Okay. All right, very quick overview. Okay, the different fastener types. We'll run through them quickly. So we have threaded fasteners. Okay, so the main ones of note for us, are going to be the bolts and nuts. Okay, and then also machine screws. Okay, so we'll see that a bolt and a nut, so that's when you go through, you penetrate, two materials to sandwich them together with a bolt. Okay, a machine screw, or the definition of a screw, is something that just dives or plunges into the material. Okay, but it's not abetted by a nut on the other end. Okay, there, as usual, many different types. I'll highlight here set screws. Okay, so we use those often, in order to set a shaft, for example, inside a collar or relative to another shaft. Okay, and of course we also have wood screws, but I want to mention them here only because the wood screw is really not an engineering component proper. Okay, it's something that belongs more under woodwork. Okay, other items in there that you see are rivets. Okay, so a rivet is a permanent form of fastener that depends upon the deformation of the part. Okay, we have washers in there that are very useful, both to keep the surface against which the head of the bolt is going to go from getting marred, and also it'll help to prevent the bolt from coming loose. Okay, pins are generally used for locating purposes. Okay, and they come in different classifications. There, the dowel pin is the traditional, fully solid cylindrical pin. In there, you have spring pins, that will allow compliance. In there, you have locating pins, with specific designs to allow for insertion into a receptacle. Okay, clevis pins, cotter pins. We'll see others here in just a second. I'll go through the various pictures. Okay, retaining rings, keys, snap fasteners. Let's look at some pictures instead. Okay, so this is the typical bolt and nut. Here in the upper right hand, you see a socket head cap screw. Okay, very, very common, although it's in this particular configuration, it does have a nut. These are set screws here in the down on the left. This would be a sheet metal screw. Okay, and then this would be more a wood screw in here. So this is would be more applicable again to woodworking. All right. We do need to concern ourselves, with different types of heads for the screws. Okay, so this would be some common categories. Would be the hex screw. So this is primarily a structural, type of device. Okay, and down here on the bottom left, the flat or cap hexagon socket. This is also known as the socket head cap screw. Okay, very, very common. And then there are very many others that have to do both with the driving type and also the shape of the head. Sometimes we'll want to bury the head of the shape, rather the shape of the head, or the head inside the material. So for that, a countersunk or a conical head is going to be very useful. Okay, we may do a pan screw, a pan head, or a round head in order to not have a full cylinder sticking out. Okay, so different options in there. Some of them may come already with a washer built in. Okay, so that could be useful. And then there are other specialty types in here. Okay, this is a picture where you can better appreciate the different driving types. So slotted, which is a truly inferior way of driving a screw. This is the original article and one that really should be forgotten. I do not recommend slotted for just about anything. Okay, Phillips makes a lot of sense. The posi drive is an improvement over the Phillips. Okay, the Torx used in aerospace extensively, and this is able to apply quite a bit more torque to the fastener. That's the name. Okay, security, that's just the same thing. With but you need a special tool. And then the hex is another very, very common type of drive shape. And what you see down here is the famed and very ubiquitous socket head cap screw. Okay. Here's some examples of rivets. We often associate rivets with structural components. They can also be used in smaller types of devices, and of course, we're familiar with those. Here we have an example of a blind rivet. So if you have access only from one side, you can still use a rivet and use a device that will deform it on the blind side, on the side that you would not otherwise have access to. Of course, that's a one-time deal, right? Here's an assortment of washers in there. We can see different types, and also notice different utilities in there. So some of maybe different materials, depending on whether you want to, again, have if you have cosmetic concerns versus fastening concerns and the like. Okay. Here are some pins. This is your typical dowel pin, wooden dowel pin, of course. This would be the steel pin, and these are usually machined, to a fair amount of precision. Okay, spring pins in there. This is a locating pin. So again, made to very high precision, has insertion features and other features that we won't go into here to guarantee precision when you are locating parts. This is an example of a clevis pin. Okay, so used for as a bearing surface, for two parts that are going to rotate relative to one another, but where the situation doesn't necessarily warrant an actual bearing or a bushing. Now, what we see here is a so-called, it would be a clevis pin, of course, as before, but with a something known as a reusable cutter pin. And here on the bottom right, you see another style of cutter pin. So these are pins that are going to keep something from moving out of place, but that are not going to be under very heavy load. So you would find a clevis pin there as a means of guaranteeing that a nut, for example, is not going to back out of its place. Okay. Some other things that we can look at in here, these are retaining rings. Okay, so these are normally attached to grooves on a shaft, again to keep equipment from moving sideways there or axially along the shaft. Okay, and those come in both external and internal varieties. You generally need a specialty pliers in here called a spanner wrench. These are keys, okay, and they're used to allow power transmission from the shaft, for example, the output shaft of a motor, to the driven shaft of, let's say, a fan, a compressor, really any type of rotating machinery. Okay, and down here we have these components known as woodruff keys. Okay, so different designs there. Okay, and finally, in the context of fastening. And I know that we've veered a little bit away, right? From the traditional threaded fastener. Okay, so here in the end are what we call snap fits. Okay, so this is another style of fastening. Here on the upper left, you have the familiar click type fastener that you would find, for example, in the strap of a bag. Now the principle is exactly the same here for this other mechanical component. Some other examples of snap fits, we're again intuitively familiar with these, from our everyday experience, and a picture of a SolidWorks strength analysis of a snap fit cantilever beam. Okay, so with this, I hope that we've given you a bit of a sense for what's out there in the world of fastening, the world of fasteners. You can imagine there's plenty more to talk about. I know that this is a common thread, right, through all this. But just as I part in here, let me leave you with this thought. It would be impossible for you to take advantage of some of these COTS equipment that we've investigated unless you knew about it to begin with. It's not you would not be able to utilize it in your design unless you knew that it existed. So really, I think that the proper approach for this is to try to expose yourself as much as possible to these things. Keep if nothing else, a curious attitude every time that you have an opportunity to see some mechanism exposed, for whatever reason. It could be the hood under your car, or your air compressor, or your HVAC system at home, something like this. I mean, anytime you get the opportunity to take off the cover, take a look, see what's there, sort of make a mental note, maybe cross-check it with a website. It's only if you know these things a priori that you can use them in your design. If you don't know that something exists, it's not possible for you to take advantage of it in your designs. So I really think that would be the right attitude, and that's what I would invite you to do.